Still going to be talking about systems of linear different. We're going to be talking about this stuff for a few days here. It's not something we're going to be done with anytime soon. Um, so let's look at a couple more examples, and also we'll talk about some important things as we go along the way. So let's say we wanted to solve the system. I like using X and Y, but other people like using X1 and X2. You should be comfortable with both, right? Whether you're using X and Y or X1 and X2, you should think of them as X1 and X2 as like X and Y. So X1/X is typically going to be graphed on the horizontal axis, X2 or Y on the vertical axis. Well, let's do one using X's and Y's because yeah. So we have the different set of differential equations. dx dt is equal to x, dy dt is equal to 4x minus y. And I'm going to give some initial conditions here. Sure, those. X of 0 is equal to 2, and y of 0 is equal to 10. Oh, thank you. Just said it right there. It's fine. As a point of interest, I'm just going to read some words here that are not super important. This type of differential equation models what's called commensalism, where one species benefits from the other but causes no harm to it. So, right, you could think of, right, for example, well, actually, so I'm not so great at this. So, right, the rate of change of X only depends on the X stuff, whereas the rate of change of Y depends both on X and Y. But specifically, X isn't harming Y here, right? If you think about like growth, as your population is increasing, it's thought of as like it's positive, your population is decreasing, it's not right. Like you want to be not harmed by growing. So that's kind of the idea here. Again, as far as I'm concerned, the biology is not that important. It's all about the math. So let's solve this system. So we're going to start with first writing in the matrix. Our equation here is dx dt, dy dt as a vector equal to the coefficient matrix, which is going to be 1, 0 for -1 times xy. And I want you to see something here that I want you to take to heart because it comes up more often than you maybe imagine. So after writing the equation, we're going to find the eigenvalues. So check this out. The eigenvalues is going to be the determinant of, again, here's the fast way we should do this. Take your matrix A, your 2 by 2 matrix, and just subtract lambda from each of the diagonal spots. So don't write like A minus lambda times I, but maybe you can write this. But then you shouldn't like take any more steps than writing just, okay, here's my matrix. It's 1 minus lambda, 0, 4, -1 minus lambda. And then we can take the determinant of that. And here's actually the thing I wanted you to see that's special about this. We're going to get 1 minus lambda times -1 minus lambda minus 0. And we're going to solve that equal to 0. Here's where you should not create more work for yourself. You've already factored this. It's already factored for you. If you get a 0 over there, whatever those two factors are, those are your factors. So just leave it as 1 minus lambda times -1 minus lambda equal to 0, and you're going to get your two eigenvalues, lambda equal to 1 and lambda equal to -1. Or, to make a long story much, much shorter, if you have a 2 by 2 matrix and you have a 0 up there or a 0 down there, your diagonal entries are the eigenvalues. End of story. So that happens actually somewhat often. Be careful though. It's only if you've got a 0 there or a 0 there, right? If you've got zeros in diagonal spots, that doesn't mean anything really. So most people are totally cool with being like, oh yes, I recognize that this matrix is lower triangular, or if it was, for example, the matrix, I'm going to call it B equal to say 3, 2, 0, -5, then the eigenvalues would be 3 and -5. most instructors are totally fine with people being like, yes, I recognize that this matrix is either lower or upper triangular, and so the eigenvalues are just the diagonal entries. Always true. So, great. Now we're going to find our eigenvectors. So let's start off with, and I'm going to call the bigger thing lambda 1 and the smaller thing lambda 2. It's pretty typical, but again, it doesn't really matter. But it is, I think it's necessary probably to actually label them as different things, just so we can keep track of which eigenvalues go with which eigenvectors. Speaking of eigenvectors, let's find them. So the eigenvectors. So for lambda 1 equal to 1, I think we should do it by solving A times the eigenvector equal to lambda 1 times the eigenvector. Let's call it V1 since we're going to call it V1. Meaning we're trying to solve 1, 0, 4, negative 1 times the eigenvector that we're looking for equal to 1 times the eigenvector that we're looking for. This is a prime example, and typically when you have one of these, either one of these lower triangular or upper triangular matrices where you've got a 0 in the lower left or the upper right corner, this next thing that's about to happen almost always happens for one of your eigenvalues. The first equation doesn't help us. If I write out the first equation here, it's 1 times x plus 0 times y equals 1 times x, which sure is true always. X definitely equals x, that checks out. But it doesn't tell you about the relationship between x and y. Y can be anything, and x can be anything as well, right? We don't know anything based on this. So this is a situation where we have to look at the second equation. We look at 4x minus y equals y. Oh yeah, that's going to tell us about how x and y are related. If I add y over there, I get 4x equal to 2y. Dividing both sides by 2, I get 2x equal to y. So I'm going to pick x equal to 1 and y equal to 2. So my first eigenvector is going to be x equal to 1, y equal to 2. I will also point out, because it is something I'm going to mention later today, this equation here, especially if you solve it for y, although even if you don't, that gives you the equation of what kind of thing? Like if you were to graph that, it would be a starts with an L. Here. Right, or just a line. Right, the graph of y equals 2x, just a line. But it's got a special name. It's called the eigenline. And it's kind of an important line if you're trying to graph the direction field, which you may or may not be asked to try to do. But I feel like he was kind of talking about that, so we'll talk about it. It would be fine if we didn't solve for y. Like if you had, 2y equal to 4x, it would still be the equation of the line. It's just easier to see what it is if you solve for y. Okay, let's find the other one. Did he talk about which way he wanted you to solve for eigenvectors, or did he even talk about it at all? Either way is fine. And again, I'm saying either way, meaning you can either do it like this, or I guess I'll do it the other way. You can do it as a minus lambda I times. Oh, I really don't want to do it this way this time, though. So I'm not going to. That's a lie. It's a big lie. It's going to do a times v2 equal to lambda 2 times v2. So if we do that here, it's going to be, again, 1, 0, 4, negative 1 times xy equal to negative 1 times xy. This system of equations, after we do this first part, you might feel like we need the second equation, and it's actually not true. So let's see what the first equation gives us. The first equation gives us 1 times x plus 0 times y equals negative 1 times x. Okay, 0 times y goes away, so we have x equal to negative x. There's only one solution to this equation. What does x have to be so that it's equal to its own negative? 0 is the only option. Right? 5 doesn't equal negative 5, 6 doesn't equal negative 6, negative 7 doesn't equal negative 7, but 0 equals negative 0. It's the only number that's neither positive nor negative. It's the only number that's equal to its own negative. If you don't like that, though, and I understand not like that, you could add x to both sides and say 2x equals 0, so x equals 0 divided by 2. Okay, now we have to remember something. What's the one vector that we said never gets to be an eigenvector? Yeah, the zero vector. Basically, the vector that doesn't have any length. The zero vector is kind of, I don't know, it's just dumb. It's important, like it's actually super important because of a lot of things about vector spaces. But as far as like a vector goes, the zero vector isn't really a vector, it's a point. It starts and ends at the same spot. It's got no length. So when you multiply a matrix by it and you make it longer or shorter by some multiple, well, 0 times anything is still 0. So it's not like it's not interesting in the way we want eigenvectors to be interesting. So if your vector can't be the zero vector, but you already know the x part of the vector is 0, what's y gotta be? Well, gotta be is what could y be? The answer is really any number you want except for 0. Usually we pick 1, but I'll point out, right, if we pick y equal to 1, then our eigenvector here is going to be 0, 1. But you could have picked y equal to 3, or 7, or a billion, or -2. And all those, since they are multiples of this vector, also classify as eigenvectors. Let me show you, just so you're all agree. So let's actually take this first. So if we do this one first, I'll point out that 1, 0, 4, -1 times 0, 1 is going to be 1 times 0 plus 0 times 1 is 0. And 4 times 0 plus -1 times 1 is -1. Which is exactly -1 times the vector we started with. But that would have been true if I did 0, 1, or really 0, comma anything that wasn't 0, even if it was 0, but I don't want it to be 0. If this is just some non-zero number, let's call it k, then we're going to get 1 times 0 plus 0 times k, which is still 0, and 4 times 0 plus -1 times k, which is -k, which gives you -1 times 0k. So if your eigenvector is 0, 1, meaning I'm thinking of the vector that's pointing straight up, right? 0, 1, 1 in the y direction, 0 in the x direction. Well, any multiple of it, meaning any other vector that points straight up, like 0, 5, or 0, 8, or actually any vector that points straight down would also be valid as well. 0, -2, 0, -7. Any non-zero multiple of an eigenvector is an eigenvector. So the point here is that you have to choose, right? There is no equation here that's going to tell you that you get y equals 1. If you look at the second equation is equally helpful. The second equation is 4x minus y equals -y. And the y's cancel, and you still get 4x equal to 0, which means x equals 0. And when x equals 0, you just have to pick y to be any non-zero thing we want, and we almost always choose 1. All right. We got our eigenvalues, we got our eigenvectors. Now let's write our solution. So, a reminder, our solution, our general solution, you definitely should memorize this, is going to be x as a vector. This is probably why people like to use x1 and x2 instead of x and y. It feels kind of weird to write x and y as a vectors x, but we do it. It's going to be c1e to the lambda 1 times t times v1 plus c2 times e to the lambda 2 times t times v2. Let's take a look. So specifically here, we're going to get c1 e to the lambda 1 was positive 1 times t times v1, which was 1, 2. C2 e to the -1 times t times 0, 1. And if we want to separate our solutions into x and y, because this is supposed to be what x in the first coordinate and y in the second coordinate is equal to, we've got x of t equal to c1 e to the t times 1 plus something I'm not going to write down because it's c2 e to the -t times 0. And my 0 looks kind of terrible there. And then y of t is going to be c1 e to the t times 2 plus C2 e to the negative t times 1. There are solutions. Our general solutions. We're still going to make them particular by finding our constant C1 and C2. There's something else I want to say here. No, it's all right. So I will point out specifically when you've got a 0 in one of your eigenvectors, it's actually really easy to find the constant C1 and C2. Let me show you what I mean. So if we're plugging in our initial conditions, which is that x of 0 is equal to, I forgot, 2, yeah, equal 2, and x and y of 0 is equal to 10. We're finding the particular solution here. Well, look at this. If I plug in 2 for x and 10 for y, I'm going to get 210 equal to C1 e to the t times 1, 2 plus C2 e to, oh, I'm plugging in 0 for t. Sorry, I forgot to plug in 0 for t times 0, 1, which is just C1 times 1, 2 plus C2 times 0, 1. And if you look carefully enough here, hope we can see it right. Everyone should be able to tell me what C1 is right now. Because we can see that C1 times 1 plus C2 times 0 has to equal 2. So we have that 2 is equal to C1 plus nothing. Oh, C1 has to be 2. There's no other choice. So when you have a 0 in one of these spots, it's really easy to tell essentially what the other constant is without doing a bunch of like writing out of a matrix and stuff. And then we can find C2 easily. We know that 10 is equal to C1 times 2 plus C2 times 1. But we know that C1 is itself 2. So 10 is equal to 2 times 2 plus C2. So C2 has to equal 10 minus 4, which is 6. So our particular solution here is that our x of t, y of t is equal to C1, which is 2 e to the t times the vector 1, 2, plus 6 e to the negative t times the vector 0, 1. I'm going to write it here as well. So this is going to give me x of t equal to 2 e to the t. This is going to give me y of t equal to 4 e to the t plus 6 e to the negative t. I feel like there's something interesting here. Check. Sure. Like that. Sorry, 1 second. Okay. I guess what are there questions so far about anything I've said or what we're doing or why we're doing it?
It's pretty similar to this like stuff that you did in 17B, right? Like, I mean,
Yeah.
like I remember doing most of this.
Yeah.
Is it gonna start like that? Is there gonna be like a
new twist?
A twist to it soon?
So what I would say is it's not so much twisty as it's kind of like what we do with it afterwards. So let's talk about kind of what we have here. And actually, so let's talk about like what our solutions mean. So again, our system, just write it down again. Our system was dx dt equal to, I forgot what it was, x, right? Was it equal to x? Sorry, I've lost my spot. Yeah, x and dy dt was equal to 4x minus y. That was our system to start off with. And our solutions with x of 0 equal to 2, y of 0 equal to 10. Our solution that we just found is x of t equal to 2 e to the t and y of t equal to 4 e to the t plus 6 e to the negative t. So there's a few things going on here that we should talk about. Trying to think about all the things I want to talk about here. Yeah. So what's happening to these populations as time goes on? Are they growing larger or growing smaller? Well, if we look over here, as time gets larger and larger and larger, so I should write some questions. So what happens as we let time go on? Well, that's really, those are just lots of words for what's the limit as t goes to infinity. So for x of t, limit as t goes to infinity of 2 e to the t is going to be infinity. Right? E to the big number is a big number. And similarly, limit as t goes to infinity of 4 e to the t plus 6 e to the negative t, well, that part's going to get infinitely large. That part's going to get closer and closer to 0. So still infinity. So both of these populations are growing larger and larger and larger, which means our equilibrium of 0, 0, right? I'll point out that our equilibrium here is still x hat equal to 0, 0. Right? If x is 0 and y is 0, then both these derivatives are equal to 0, which means things aren't changing. Those equilibria are unstable. Right? If we move even a little bit away from them, our arrows are going to point outwards away from the origin. I will point out specifically this type of instability is called a saddle. And we know it's a saddle, or we will know it's a saddle because one of our eigenvalues is positive and one of our eigenvalues is negative. So if you get two real eigenvalues that are different signs, it's a saddle. Because one of our eigenvalues is positive and one of our eigenvalues is negative. Whereas in the last class, both of our eigenvalues were positive and we had what was called an unstable node. Don't worry if you don't remember that. We're definitely going to go over all the classifying probably on Wednesday. What else did I want to mention here? Yeah. So I think your teacher cares about you being able to draw these things, or at least kind of know what the drawing should look like. So we're going to try and sketch this direction field. And I definitely saw that he was talking about how, so he was pointing out that in this case, your dy dx, the slope of your vector, the slope of your direction. I don't want to say the slope of your tangent line because we're not like drawing, but technically it kind of is the slope of your tangent line. The problem here is that there's a lot of different solutions, and we're going to see that in a little bit, but I'll point out that the slope of your tangent lines are just your dy part divided by your dx part. So as long as you don't choose 0 for x or 0, but you can see like at the point, for example, at the point 1, 1, the slope is going to be 4 minus 1 over 1, which is 3. And at the point, I'm just going to pick a few values here just so we can kind of, we'll verify this in a minute here. If you plug in, say like 1 and negative 1, you're going to get 4 plus 1 over 1, which is 5. So you can see that depending on where we are in the plane, we're going to get different slopes, which again, not too surprising. But how are we going to graph this thing? Oh, well, so how to graph the, what do we do? I always forget what the direction field, the phase plane. I never know the right words for this thing. I think it's the phase plane. How to graph the thing. We'll fill that in. Whatever it's called. We'll leave ourselves in space there. Okay. So I think there's two things we need to focus on here. Thing one, the eigenlines. So if we go back here, eigenlines. In other words, the line that contains the eigenvector. So These are just lines that the eigenvector lives in. So for the eigenvector, let me make sure I get the right way here. Don't want to screw it up. For the eigenvector 1, 2, you should just think of that as your rise over your run, where the rise is the y part and the run is the x part. So the slope of this line is 2. So the eigenline is going to be y equal to 2x. For the other vector, it's kind of weird. For v2 equal to 0, 1, that's an infinite amount of rise over no amount of run. Or you can just think you're going straight up, right? So that's going to be the line x equal to 0. It might even help if you graph them, right? For the vector 1, 2, I'm literally going over 1 and up 2. Oh yeah, I can see that if I'm trying to draw the line through that, that's totally the line y equals 2x. Similarly, if I try to draw the line that goes from the origin to the point 0, 1, oh yeah, that's just the line that goes straight up and straight down, which is x equal to 0. And we're also going to draw the null lines. So the null lines are just the lines you get by setting each of the differential equations equal to 0. So our first differential equation was dx dt equal to x. So this one's kind of annoying, boring, I don't know. Annoying in that one of our null lines also happens to be the same as one of our eigenlines. That happens sometimes. Not all the time, though. So I want to point out that on this null line, there'll be absolutely 0 horizontal change because the change in the x direction is 0. So all of my little lines I draw along this line are going to have to be pointing straight up or straight down. This null line, we point up or down, but no tilted left or tilted right at all. Similarly, for the other null line, dy dt equal to, what was it, 4x minus y? Well, I'm going to solve this for a way that looks more familiar to me. I'm going to write y equals 4x. On that straight line, all of my little segments are going to be purely horizontal because there's absolutely no change in the y part. The rate of change of y is 0, meaning all of my slopes of my tangents are purely horizontal, no vertical component at all. So all of my things point that way or that way. Okay, so now we're going to try to draw this thing. You know what? I used to have a little tiny ruler and I left it somewhere. I don't know where I left it. I'm sad that I don't have it because it's a great little ruler. So yeah, so there we go. 1, 2, 3, 4. I'm going to try and make this somewhat not terrible to draw. So yeah, I'm really wishing I had that ruler. So I'll draw my eigenlines here. Sorry, my null lines. Sorry, so here's, yeah, that one's pretty steep. When you draw these things, don't draw arrows at the ends, even though it's really kind of what we usually want to do. So there's my null lines, null line where dy dt equals 0. So along this null line, all of my little direction arrows are going to point horizontally. I don't know if they're pointing left or right yet, but I'm just going to draw them in like this. And then, unfortunately, the other one is kind of unexciting. There it is, right there. Along this, dx dt is equal to 0. So that means all of my lines have to point vertically. Now they're already kind of on there, so it's kind of silly to draw like lines like this and that, but there they are. I drew them. You can see them, right? And then we also have our eigenlines. So one of them we already have, right? So here's the thing about an eigenline. Any of the vectors along the eigenline. So remember, what happens with an eigenvector, when you multiply the matrix by the eigenvector, you get another vector that points in the same direction or the opposite direction, right? It's along the same line, right? The matrix times the vector equals a multiple of the vector. So let me draw that over for sure. So drawing the other eigenline, which was y equal to 2x. Give myself a little more room here. Again, don't resist the urge to draw arrows at the end here. So here's my eigenline y equal to 2x corresponding to which eigenvalue? Good question. Corresponding to the eigenvector 1, 2, which came from the eigenvector. The bigger eigenvector, the positive one. This one corresponds to lambda 1 equal to positive 1. And this eigenline here, which is the same as this nullifying here, is x equal to 0, and it corresponded to lambda 2 equal to negative 1. Okay, here's what this means. Lambda being positive 1 here means that when you take the matrix and you multiply it by a vector, you get exactly 1 times that vector. So in this case, it gives you back the same vector you started with. So any vector along this line, after you multiply by the matrix, should end up pointing in exactly the same direction along that line. So that means our vectors along this line point outward, away. Because we're just kind of seeing what the matrix does to the vector. And the eigenvalue tells us, oh, the matrix gives you back the same vector you started with. So I plug in a vector of say like 1, 2, I get back a vector of 1, 2, pointing in exactly the same direction. Okay, but if we look over here, along the line x equals 0, our eigenvalue is negative 1, meaning that if I plugged in the vector, say 0, 1, I would get back the vector 0, negative 1. It would be pointing in the opposite direction of the direction I started, meaning my vectors are all going to point inwards towards the origin as opposed to away from the origin. So up here, we have all of our little arrows pointing in. But I really, really, really want to stress. Let's let the equations again over here just for a moment. So my dx1, sorry, my dx, I wasn't using x1 this time. My dx dt is x. My dy dt is 4x minus y. Yeah, 4x minus y. Let me point out to all of you, right? If you plug in 1 for x and 2 for y, you're going to get out that dx dt is 1 and dy dt is 2. So if x equals 1, y equals 2, we're going to get back that dx dt is equal to 1 and dy dt is equal to 2. So if we start right here, we're going to point exactly that way. And similarly, if we plugged in, say, like x equal to 0 and y equal to 2, dx dt would equal 0, and dy dt would equal negative 2. So if we start at the point 0, 2, we're going to be pointing in the downward direction because our vector is 0, negative 2. All this to say, on the eigenlines, all the arrows have to point exactly towards the origin or away from the origin, but not in a direction that is skew from the line itself. So along the eigenline, all the vectors point parallel to the eigenline or along the eigenline. I feel like I'm saying it in all the ways I can. Whereas on, say, these null lines, the arrows don't point in the same direction. Right? The arrows, right? The direction here would be pointing towards the origin, right? Because all the lines go through the origin here. Here we're pointing left or right. Left or right. So then the job becomes, okay, I want to try to figure out what's happening here. So let's say we pick a starting point like up here. Okay, well, if I pick that starting point, which way am I getting pushed? Well, I could plug it in, right? Like this could be like 0.5 comma something. If x is 0.5, well, my dx dt is going to be 0.5. And if x is 0.5 and y is some large thing, it's probably going to be negative. So I'm pushing right in the positive x direction and down in the negative y direction. So I'm going to come down this way, but then I'm going to have to cross this null line purely horizontally. And then I'm going to stop going downwards and change directions and start going upwards. And then the eigenlines are kind of like asymptotes, right? Because you can't actually end up on an eigenline, because if you were on the eigenline, you'd have had to stay on it. So you get asymptotically closer to it. So if we started there, we didn't going that way. If we started, say, like, I don't know. Actually, let's plug in the point. So if we start when x is 3 and y is 1, well, if x is 3, dx dt is 3, and if x is 3, dy dt is 11, right? 12 minus 1 is 11. So here we're going right and up, but more up. So we're kind of going that way, like that. And if you keep kind of filling this in, you end up getting something very, very saddle-ish. So you have like things going like that. You have things going like this. You have things going like this. Basically, I'll trace it the right way. The null lines tell you how you can cross them. I didn't really do a good job of crossing any of them. Well, the problem is one of my null lines here is also an eigenline. So the null lines can be crossed, and the eigenlines are serve as like your asymptotes that you get closer and closer to. I know I'm kind of saying a lot of things. I'm not giving a whole lot of description here, but it does take some kind of practice getting a feel for what's happening. So I'll remind everybody here, our lambda 1 was 1, which is positive. Our lambda 2 was negative 1, which is negative. And we ended up having a saddle, which I kind of think of as in one direction, you're kind of rolling into it like you would, like you're kind of stable in one direction and unstable in another direction, which is actually extremely true here. If you happen to, if you had started on the x-axis, sorry, on the y-axis, you would end up getting pushed back exactly towards the origin. But if you deviate just a little bit from the y-axis on either side, you're going to get pushed way away. So that's why a saddle is called unstable, even though technically there is a direction of stability. Okay, what else to say about this? I think I had one other important thing to say here. I thought I always did, but I guess. Nope, I guess not. Okay, so let's look at one more example, which we may or may not finish, but I do think it's worth starting. So let's say, we'll do one more example and we'll work through it kind of quickly because, well, we want to be able to work through them kind of quickly. So let's look at the following example. Yeah, another example. We have let me use x1 and x2. dx1 dt is equal to negative 2x plus 2x1 plus x2. And dx2 dt is equal to 2x1 minus 3x2. All right, so let's solve it. I do want to remind everybody, 0, 0 is our equilibrium here. For this homogeneous system of equations, homogeneous just means like 0, 0 is a solution. You can write this as a matrix times xy and or x1, x2, and there isn't like another vector you have to add on. So this is our equation, dx1 dt, dx2 dt equal to negative 2, 1, 2, negative 3 times x1, x2. If there was like some other piece I had to add on out here, like if I had like a +5 up here or something, then it would no longer be homogeneous because 0, 0 wouldn't be the solution of the equilibrium. But here, this is a reminder to everybody, x hat equal to 0, 0. is the only equilibrium. It's the only value of x1 and x2 that make both of these equations equal to 0 at the same, same time. All right, let's do all the things. Not a nice situation for the eigenvalues here, right? Unlike the previous examples, we have to actually find them. So we're going to do the determinant of -2 minus lambda, 1, 2, -3 minus lambda. That's going to be -2 minus lambda times -3 minus lambda minus 1 times 2, set that equal to 0, multiply it out. You get lambda squared plus 3 lambda plus 2 lambda is plus 5 lambda plus 6 minus 2. That simplifies as lambda squared plus 5 lambda plus 4 equal to 0, and that does factor. It's lambda plus 4 times lambda plus 1. So in this case, both of our eigenvalues are going to be negative. And just knowing this alone, if you think about what the general solution looks like, you should be able to justify to yourselves that this equilibrium will be stable here, because both of our x1 of t and our x2 of t will be something e to the -4 times t plus something e to the -1 times t. And as t goes on and on and on, the x1 is going to get more and more negative, which means e to the negative whatever is going to get closer and closer and closer to 0. So when both your eigenvalues are negative, that means we have a stable equilibrium. In this case, what's called a stable node, because they're both. So just for future language stuff, you get nodes when the eigenvalues are real. So both positive, unstable node, both negative, stable node, one of each style. When the eigenvalues end up being complex, which we'll see very soon, your equilibrium will be either a stable spiral or an unstable spiral, as opposed to being a node. When you think of a node, like stable node, I think of it, it's called a sink also. Kind of think of like all the water draining into the sink. It's stable, everything's going into it. Whereas an unstable node is the source, everything is kind of spewing from it. It's right from the source. It's the difference between it's usually called the faucet. The faucet is the unstable node, everything's coming out of it, and the sink is the stable node, everything's going into it. And then this saddle is just terrible. Okay, let's find the eigenvectors. Yeah, we have enough time. Probably, maybe, sure. So eigenvector 1. Oh, we'll do both. We'll do these the fun. We'll do one of each of these. So for lambda 1 equal to -4, we have our matrix -2, 1, 2, -3 times the vector we're looking for equal to -4 times the vector we're looking for. Using the first equation, I'm going to get -2 times x plus 1 times y equal to -4 times x. Add positive 2x over there, you get y equal to -2x. So that's going to give me an eigenvector of x is 1, y is -2. Or take your pick. Usually if there's one negative, people kind of, like some people might say it's -1, +2, but those are both standard choices here. For the other eigenvalue, we'll do it the other way. Instead of doing a times your eigenvector equal to lambda times your eigenvector, we're going to do it as, this is why I don't like this one as much, but here we go. -2 minus -1, 1, 2, -3 minus -1 times the eigenvector I'm looking for equal to the 0 vector. This is also an option. It's the option where you're doing a minus lambda I times your eigenvector equal to the 0 vector. Both are an option. For whatever reason, it feels like most instructors prefer this. I couldn't tell you why. I think this is much nicer as far as telling us what's happening, telling you when you multiply the matrix by a vector, you're just getting a multiple of that vector. I think that's nicer, but it's just me. So then, looking at both my equations here, -2 plus 1 is -1. So that first equation is -x plus y equals 0. The second equation is essentially the same, right? It's 2x minus 2y equal to 0. We're just saying y is equal to x. So here my eigenvector is the vector 1, 1. General solution. I did not give initial conditions, right? I never said x1 is 0 and x2 is 0 or anything. So just the general solution here is going to be x1 of t, x2 of t equal to c1 e to the lambda 1 is -4 t times my v1, which is 1, -2, plus c2 e to the -1 times t, so -t times the vector 1, 1. I think it's good to be able to write your solution both in the vector format like this, and also as each individual x1 and x2 separate. So let's write it that way as well. So here we'd have x1 of t would be equal to c1 e to the -4t plus c2 e to the -t. And x2 of t would equal -2 times c1 e to the -4t plus c2 e to the -t. And I think you can all agree that if we let time go on and on and on, both of these terms are going to get smaller and smaller and smaller. So both of these go to 0 as time goes to infinity. Which means our system is stable, because as time goes on and on and on, the value of x and the value of x, so the values of x1 and x2, whatever those populations represent, are getting closer and closer to 0. Maybe not the best, maybe it's not like, I feel like we've kind of phrased it as stability sounds like it's great and instability doesn't really mean anything as far as what's good or not. And that's really kind of a very qualitative, right, assertion that doesn't really matter here. But just we see that, okay, stability means the populations are eventually dying out. At least that's one interpretation of it. We probably don't have enough time to do that. See if there's anything else I want to say here before I go on. Yeah. So we would call this a stable node, also known as a sink. And yeah, I would love to try and draw it for it. Let me just show you the drawing that I already have, since I don't really have enough time to reproduce it for you. So here's the drawing. Let me show you. We can talk more about this on Wednesday. But essentially what we've got here is we have our two null clines in red and green. The red null cline where the first equation equals 0, that's going to be y equals 2x. And the second null cline where 2x minus 3y equals 0, or that's going to be y equals 3 halves x, which is this green line here. And then in blue, we have the eigenlines. So we have the vector 1, 1 for lambda equal to -1. And we have the vector 1, -2. So 1 left, 1 right, 2 down, yeah. And both of those have arrows pointing inwards because the eigenvalues are negative. Right? If you start at a point like this, if you plug in something like 1 for x and -2 for y, and you plug this into these equations here, you're going to get back a vector pointing towards the origin. So that's why our things point that way. And yeah, I don't think there's a lot more to say about that. I think trying to feel like if there's anything more I should really say here. And then you can start at any point you want. So if you start here, you get pushed by kind of say, well, we're going that way, we're going that way, and I have to cross this line vertically. So I can't come at it like that. I have to kind of go this way, cross it vertically, and then get pushed towards the origin. But you can start a lot of places. Like, for example, if I started right here, I know eventually I'm going to cross that line like that. It takes practice for sure. But again, I'll say the guiding light when if you're trying to draw these, and I don't know how much trying to draw these is going to have you do, if at all, but if you are trying to draw them, you're crossing null clines and you are asymptotic to eigenlines. That's, in my opinion, the best way I can say it. All right, 201, stop talking. Office hours as usual. I think on Wednesday we'll start classifying. We'll talk more about just the classification, because a lot of the time what we do is actually like, here's a system. Don't solve it. Just tell me what the solution or what kind of equilibrium we have, whether it's a stable node, an unstable node, a saddle, so on and so on and so on.
I have a question.
Yeah.
On the very first page, Did you say that as long as there's a zero in the matrix, the diagonals or the what? Or
Not quite. Let me clarify that. So as long as you have a zero either in the upper right-hand corner or in the lower left-hand corner, then and only then can you say that the diagonal entries are the eigenvalues.
wait, perfect. Thank you.
Go.